Okay, the fundamental theorem of calculus actually is two theorems. So I will show the first one. The first one said that let f be integrable on AB for each x in between of the closed interval. Then it means if it's integrable, is that I can do basically the integral as we have here. Then f is uniformly continuous in that closed interval. Furthermore, if f is continuous at c, any c in the closed interval, then f is differentiable at c. And basically we can write that if a capital F prime here on c will be equal to the evaluation of x of c, right? We have to recall a few properties of integrals that they are actually easy to prove. This is a homework for you guys to do it. If we have the integral from b to a is the same as the opposite sign of the integral from a to b of this function, right? The function, the integral from a to a, basically is the area from a to a. There is no area there, so the integral is 0. Same thing from here. If we have a point C in between of A and B, we can write the integral from A to C of S plus the integral from C to B of F. Okay. Also, this is super easy also to prove. This is from the triangle inequality, that the absolute value of the integral from A to B of F is less or equal to the integral of a to b of the absolute values of s, right? So let's prove the first part. Remember that here we have two things that we have to prove. One is the uniformly continuous, right? And the other one is that f is differentiable at c, okay? So the first one, this is I think the easiest one that we can have. Since f is integrable in this closed interval, then it is bounded. I mean, that is coming from the definition of integrable, that we can bound the function, right? It's not going to infinity. We have a bound, a b, that is greater or equal to the absolute value of all the f x, the evaluation of x of in the function f for all the numbers that we have in the interval, right? So then let's have epsilon that is greater than 0. Suppose that we have that as a given number. Then for every x and y that belong to the closed interval a and b, of course x be less than y, right? We have that the distance in between them will be less than epsilon over b. Why epsilon over b? We will see it in a moment, right? But we can have basically, I know that this number is greater than 0, and that is what matters right now. Then if we have the absolute value of these two numbers, these two functions evaluated, the capital F evaluated at y and capital F evaluated at x, is equal to, again, the absolute value of his integral representation, right? And here we see that, okay, we have the a in both sides, right? We have x and y that we don't repeat, but we can move this a to the top and change the signal, right? So the sign, sorry. Then we move this to the front and this to the right, like we have it here, x and a to y. So we can write this two sum of integrals as just one integral, that is the integral of the absolute value of the integral of x to y and the same function f of t, right? And we know that by the triangles inequality, we can write that this is less or equal to the integral of the absolute values of the function, right? And this function, we know it is bounded. It's bounded, it's by definition, it's bounded by a number b. So this function is less or equal to the same integral of b instead of the function, right? B is a constant. So we basically have the remainder is dt. And dt, I mean the integral of dt evaluated in these two numbers will have equal to b multiplied by the difference between y and x, which we already say that if we have that this e is the division by b, we can basically cancel this b and multiply it by the distance between these two numbers, and we will have epsilon. Therefore, x is uniformly continuous. Okay. Now what? The second part of the fundamental theorem of calculus 1 is this. We want to prove that f is differentiable at c, right? And basically this is that is what we want to try to prove, that the difference between when I take the derivative of capital F evaluated as c is the same as I evaluated f of c, right? We should recall that the derivative is the limit of this difference, right? Basically this is the difference of the evaluations divided by the difference of the numbers that we want to approximate, right? Then that is correct if and only if for every epsilon greater than 0, I mean I am calling the definition of a limit, right? The limit is this: we have an epsilon greater than 0, may find a delta also greater than 0. So for every x that belong to this interval with the distance greater than 0 but less than delta, we have that the absolute value, right, of the difference between whatever we have in the limit, right, minus what we say that it is the limit. We say that this limit is equal to this. Okay, we remove that. The absolute value of the distance of that will be less than epsilon, right? Then let's see what is exactly this part that we have inside. That is what I wanna see. So then we see this. We can extract this this number. This is basically a constant number, x minus c, right? I'm sorry, this is not a constant number. C is a constant number, and we can move that outside like we have it here, and we just multiply it by whatever we have in the denominator. Let's subtracting to that also the 1 over x of the function c. Where this is coming from? You are maybe asking if I already have this evaluation of function, which is a constant. Why I am writing this like that? Okay, let's see this part. If I see, basically I am multiplying by 1 to this, right? If I multiplied f of c by c, by the integral from c to x of t of dt, we will have this difference, right? And so if I want to remove this from the difference, I need also to multiply it by 1x over c, right? So basically this one will cancel with this one, and finally we will have only f of c. So I am doing just a multiplication by 1 here, but putting in this form so that I can work with the integrals. Okay, Now that I have these two terms at the front of every of the other ones, I can move this outside of the this difference also carry on with the absolute value, and I will have, again, I just put the definition of capital F is the integral, right? So I put the integrals here in this form, and I have also the integral from f of c. Again, we see that we have the a and the a. I can also change the sign here and move this ahead, and I will just write all this as a one integral, which is this one, right? And then what? Oh, these two integrals have the same numbers here in the definition, right? They are going from c to x. They are the same differentiable in dt, right? So I can write this also as a one integral, and we will have basically this one. This is the common factor that we move it out. Just one integral with the difference here, differentiable on t, right? But we said, okay, we can't move this absolute value inside of them, and we will have that they are less or equal, and this is because the triangle inequality, the same common factor at the beginning multiplied by the integral from c to x of the absolute value that we move it inside of this difference, right? But this difference, we said that this is less than epsilon by definition. This is what we have proved also previously. So we can have that all this is less than this, the absolute value of this common factor multiplied by the integral from c to x of epsilon of t, right? And this is a number, a constant number, so we can move it outside, and basically this integral of differentiable of t will be just the distance from x to c, right? Multiplied by the epsilon, but this one we can move, we can cancel, and we will have this equal to epsilon. Therefore, the capital F evaluated at c is equal, I mean, this is not the capital F, this is the normal function evaluated at c is equal to the derivative of the capital F evaluated at c.